Today we are going to do the second lesson for Unit 5, and today's topic is a pair of things. They're called combinations and permutations. They are related but different, so we will talk about each of them in turn. To start out with, you will see that the start of the notes today talks about ordering sandwiches. So maybe you've been ordering in from different restaurants. This was off of the Subway menu, and so suppose that you wanted to order some sandwiches. So according to the menu I found online, these are the different kinds of bread you could get. So there's 1, 2, 3, 4, 5, 6 different kinds of bread. And then you can see that for meat, there are 14 options because there are 13 kinds of meat, or you could choose to have none. And then for cheese, there's 5 kinds of cheese or none. For the veggies, there are 11 kinds of veggies, and for the sauce, there's 8 kinds of sauce. So I know this isn't realistic in terms of actually going to Subway because, for example, you could have a lot of different kinds of veggies put on. But let's just suppose that for whatever reason, maybe there's a new rule, maybe you just decide you are going to be able to pick one kind of bread. That's pretty normal. But I'm going to restrict you to picking one of these, one from the cheese group, one from the veggie group, and one from the sauce group. So let's just say you could only pick one per category. And my question to you is, how many different kinds of sandwiches are possible? Okay, so that's going to be what we're going to ultimately figure out. For now, I'd like you to actually write down what you would order, just for fun. Okay, so for instance, my favorite order, let's see, what do I feel like today? I usually get the 9-grain honey oat. I feel like a little bit more grain is good. I would, out of the meat, sometimes I get none, but sometimes I would get like the tuna. I would get provolone. I would choose probably spinach for my veggie, and I would choose none for my sauce. That's already enough, good enough for me, okay? So that would be my choice, okay? So the notes are a little bit strange because I wrote these for last fall and we were obviously in class. And so the first question says, compare your sandwich choices with the person next to you. How many things lined up? Like, did you have the same bread or did you have the same cheese? Now, obviously we can't really do that right now. And so as a class, if we were all together in one space, would you think that people would have the same sandwich? Maybe, but it seems unlikely, okay? And the reason that it seems unlikely is because there were so many choices. So even if you order something that's pretty common, like I think the spicy Italian maybe is kind of common, maybe the meatball sub is kind of common. Even if you pick something that's pretty common, it's unlikely that that person also picks the same cheese and picks the same vegetable and picks the same sauce. Okay, so if you look back at the menu, as I presented it, there were 6 kinds of bread. There were 13 kinds of meat plus no meat. So there's 14 choices that you could make it for that one meat, 6 choices you could make relative to cheese, 11 different vegetables, and 8 kinds of sauce. So if my question is, well, how many sandwiches are possible? Understand that I'm going to pick bread and meat and cheese and veggies and sauce. Now I'm emphasizing the word and there because we know that in probability type questions, and indicates something. And indicates multiplication. And that's unlike other math. Other math usually and indicates addition, but in probability life, that small word and usually indicates a multiplication. And so here, if we multiply out 6 times 14 times 6 times 11 times 8, we get 44,352 different possible outcomes. And that was even restricting you from having multiple vegetables. Like if we were to allow you to have multiple kinds of cheese, multiple kinds of meat, multiple kinds of vegetables, it would be even more sandwiches than that. So that's why I said it was pretty unlikely that within our class or group of classmates that we would have the same sandwich. Now, a lot of time, the reason that we're figuring out how many possibilities there are is because we want to use our definition of probability. And we've been using this now for over a month. So like, I feel like you really do know this, but I just am reminding you that when you want to find the probability of something, you take the number of ways that something can happen over the total number of outcomes in the sample space. So if I wanted to know the probability that someone picked my exact sandwich, Well, that's one exact sandwich out of the 44,352. That is incredibly unlikely. In fact, when I do that on my calculator, I get this really weird outcome, this really weird thing on my screen. I get 2.254 then an E, and then a -5. Okay, so I hope we know that that means scientific notation. This E -5 means that I want to put this decimal point 5 spaces back. So that would be 0.00002254. That's the probability that someone picked the same sandwich as me. Right, if you assume that all the sandwiches are possible, are in your sample space. Okay, so let's just imagine that it's now May, right? It is now May, in fact. And say that you've made your college decision, yay! And let's say that you get to go to campus for orientation, yay! And one of the things that they do is they have you go to a session where you get set up with your technology. And one of the things they want you to do is to set up a new password. Now, this example is kept a little bit on the easy side compared to what would actually happen, because you would probably have a much more robust password. But I've made a pretty simple example here, just so you can see, like, even with this kind of unrealistic password scenario, you still get quite a lot of different options, which is why passwords matter. So let's say that they wanted you to have a password that was 6 characters long, and they said it has to be 4 letters followed by 2 digits. Okay, so for example, I might pick the name of my dog. My dog is actually named Lexi. This is what happens when you let your children name the dog when they are very young. So none of us thinks the dog should be named Lexi at this point, but when my kids were little and our dog was a puppy, this is what they thought would be a really excellent dog name. It's fine. It's fine. I think they both had friends named Lexi at the time. Anyway, so Lexi, and let's say I said the next 2 digits are going to be 42, 4 and a 2. Okay, so that would be one possible password, just to make sure that you understand what I mean. Okay, so the math question of this is how many possible passwords could be written if you are able to have repeats. Like, let's say I could have XXXX or 77 as my number at the end, right? So if you can have repeats, then there's 26 different letters of the alphabet, and all 26 of those letters are available for each of these. And then how many different digits are there? If you said 9, you're close to right. There's 10 digits, right? Because you can have a 0. So this could be 10 different options, and this has 10 different options. So I'm picking all of these, right? I have a letter and a letter and a letter. Notice the and. That means you're multiplying. So when I multiply those together, I get 45,697,600 different options. And that is actually, think about, like, when you make a password now, don't they often say, like, have a special character, have a capital letter, have a this, have a that, right? And they don't specify a certain number of characters except for saying it has to be like 8 or more or something like that, right? So this is a very, very simplified and unrealistic scenario, because they're never going to tell you to have a shorter password or tell you you have to have letters in these slots and numbers in these slots. But even with those unrealistic constraints, you already get 45 million different possibilities. So why passwords are great, okay? Now the next question says, how many passwords could be written if you can't have repeats? Well, if by putting an L here, I could not have an L somewhere else. This first slot would still have 26 options, but my next letter can't be the same as the first. So it has one fewer option. And the same thing down the line if repeats are not allowed. Then when I get to the number, there are 10 different possibilities, but whatever number is here cannot also be used here if you cannot have repeats. So then this would be 9 instead of 10. Now that is clearly going to be fewer possibilities. which is why we usually don't have that constraint in passwords, right? We want to have more possibilities, not fewer possibilities, but that would be the math. Okay, so what we just did is actually what we would call a permutation. A permutation is where order matters. So what I just wrote here is that it's a listing of objects in order. Okay, so as an example, how many ways can you arrange the letters A, B, and C? Well, if we just did this like figuring it out ourselves, I'd start out with, okay, if A is first, I could have B and then C. Or if A is first, I could have C and then B. And then those are the only ones that have A first. If I had B first, I could have B, then A, then C, or I could have B, then C, then A. And if I had C first, I could have C, A, B, cab, or I could have C, B, A, and that's it. So there would be 6 different permutations. So permutation is writing them in order, right? List, 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 like in order left to right, okay? So a way of writing this is going to be with factorials, okay? So I could say in this problem, there are 3 different letters that could be in this first position. There's, after I pick that, then there's 2 different choices for this second position. And then there's only 1 choice left for the last one because I only have 3 letters. So the short way of saying 3 times 2 times 1 is actually 3 with an exclamation point, and that's called a factorial symbol. So 3 factorial. 3 factorial means 3 times 2 times 1, which is 6. So in the little box down here, we have that definition, right? So if I have n objects and I want to put all of them in a list, the number of ways that that can be done is n factorial. Okay, so here's the graphing calculator, and I just wanted to show you where that is on your calculator. So I'll just type a 3, and then here in math, if you go over to probability, there is an option for the factorial symbol. And if you just hit enter, then it does that math. Okay, you might say, no, why wouldn't I just type 3 times 2 times 1? You're right, that would be pretty quick. But sometimes you have like 44 factorial. You don't want to have to type all that out. Okay, our next example was about the Winter Olympics. So at the 2014 Winter Olympics, 6 finalists qualified for the medal run in the freestyle moguls. During the finals, the order of the skiers is not determined by their previous scores. It's entirely randomized. So it's like putting the names in a hat, so to speak, okay? So in how many different orders could the finalists ski? Well, there's going to be 6 skiers. And there's 6 different options for this lot. But then once that person is picked to be the first one, once their name is drawn from the hat, there's 5 left for the next. And then there are 2 names have already been drawn out of the hat, so there's 4 left, then 3, then 2, then 1. So as we just were talking about, this short way of saying this would be 6 factorial. And if you type that on your calculator, that's 720. Now they're wondering about the ending of the race. So there's 720 different options for the start of the race, like the order in which they might go down the run. But medals are only given to the top 3, right? The gold, silver, and bronze medal. In how many different ways can 3 of the skiers finish? Well, there's 6 different skiers that might be in first place. Once one person crosses the finish line, there are 5 skiers who are still competing for the silver. And then once the second person finishes, there's only 4 people in contention for the bronze. So this is 6 times 5 times 4 is 120. And this is an example of something called a permutation as well. It's just that in this case, I started with 6, but unlike here where I picked all 6, I only picked 3. So the first guy we would write like this: 6, a permutation of 6 things, choosing all 6 of them. This is a permutation of 6 things, choosing just 3. Okay, and that's going to be defined right here. Okay, so there's a formula down here. Let's make sure I've crossed all my T's and dotted all my I's. Okay, so in the last example, we took 6 steers and grouped them 3 at a time. I guess I actually just wrote this on the previous slide. Sorry about that. Okay, and so the way that you can figure this out, as we just saw, was to do 6 times 5 times 4. And the reason that that works is we're really doing 6 factorial over, and then if you take this, 6 minus 3 is 3 factorial. And if you look at how that would mechanically work out, if you had 6 factorial on the top and then 3 factorial on the bottom, these would all cancel, which is why our math was just 6 times 5 times 4. So here's our formula. If I had, say, 10, permutation of 10 things taken 4 at a time, that would be 10 factorial over 6 factorial. You subtract these, and that's the factorial that goes on the bottom. Okay, just for clarity. All right, so suppose back in the day we were all in school together. Suppose you were sitting in class, not checking your phone during class. Good job. And when you leave class, you notice that you have 6 Snapchats on your phone. In how many orders could you reply to each of the 4 Snapchats or to all 6 of them? And keep in mind, in this math problem, we are thinking of answering each of those individually. Okay, take a second and see what you think. Okay, I'm going to have you pause the video, solve the problem, come back in a minute. Okay, I hope you tried the question yourself, but this is the setup. So you have 6 different ways of answering. Those are 6. Oh, sorry, I'm saying this very badly. Okay, just got tongue-tied, sorry. So there's 6 different messages that you need to reply to, and you're going to reply to 4 of them. So that means you'd have 6 factorial over, and then 6 minus 4 is 2, so 2 factorial. So you could write that out like this. Or you might have just said, I need to do 6 times 5 times 4 times 3. That's fine. 6 factorial on its own would be if you were replying to all 6. But the question asked, how many ways can you reply to 4 of the 6? All right, so there's another scenario we need to talk about, which is when the order doesn't matter, right? In the previous question, it asked for how many orders in which you could respond. And in assigning medals for the ski race, obviously the order in which they finish would matter, right, in terms of winning the medal. But sometimes the order doesn't matter. Sometimes just having a subgroup matters. So a classic example in my head anyway is like the math department has 19 math teachers, and there might be like a new committee, and our department chair might say, hey, I need 3 of you to be on this committee. That's not a situation where order matters. It's not like, oh, you're the first person on the committee, you're the second person, you're the third person, and that order is somehow differentiating anything. It's just that we need a small group from a big group. Okay, so that is what's called a combination. Okay, when the order doesn't matter, there's going to be fewer options because, I don't know why I wrote an S on that. There are going to be fewer options because, like when we were listing out before, like the A, B, C, C, B, A, all of that, these would all be considered the same combination, right? There's an A, there's a B, there's a C in every one of those, okay? So when order doesn't matter, it just matters which things are included versus not included, okay? The formula for this is right here. So when I have a combination, I'm going to use a capital C instead of a capital P. There's still the factorial for this, and there's still subtracting this and putting that as a factorial here, but there's also an additional R factorial. You need to divide out the things that have the exact same elements, and so there's going to be fewer of them as compared to the permutation. So let's look at some examples. So this says count the number of combinations of the given number of letters from the list. So these are 6 letters. So how many two-letter combinations could I make? Well, that would be 6C2, or 6 combinations, or combinations of 6 things taken 2 at a time. Sorry, I'm very tongue-tied. Okay, so that's going to be 6 factorial over, and then subtract these, 4 factorial, and then 2 factorial. So if I were doing this by hand, I would do this, and then 4 factorial, and then 2 factorial. Now this is going to be kind of nice because a lot of stuff cancels right there. And then I have 30 over 2, which is 15. So you can see that math isn't all that bad when the numbers are small. When the numbers are big, I definitely do want to make use of my calculator. So let's take a look at that for a second. Okay, in the calculator, there's actually stored formulas both for permutations and for combinations. So if I were to type 6, oh, actually, I might not have wanted to type 6. Let's see. I forget what version of calculator I have right here. Oh, okay, it was all right. So let's start from the start. Okay, so let's say I just did math and I went over to probability and then to item number 3. Okay, I might then type the 6 that I had in that last question and then the 2. And there's my answer from the problem that we just did. Also within math, you might have seen it while we flipped past there. In the probability, there's also the thing for permutations. So if I wanted to go back there and do a permutation problem, I certainly could do that. We had the 6 skiers and 3 of them were going to get medals. And that was our answer from before, right, 120. So all of this is actually stored in your calculator as like formulas themselves. I do think it's nice for you to know the formula yourself also, just to double check, right? Having more than one way is like good backup. Okay, if I were choosing 3 letters from this list, how many ways in which could I do that? That would be 6 factorial over 3 factorial times another 3 factorial. When you do that math, you should get 20. For 5 letters, that would be 6 factorial over 1 factorial times 5 factorial. That's just going to be 6. Okay, you should be able to do this both writing out something like this and working on your calculator. Okay, I'd like you to try both of these on your own and then come back in a second to check your answers. Okay, so in closing, you can see what your answers should be. These were all based on combinations. So 66, 31,824, and then 6 and 7, if you struggle to put that into writing, you can just see the sentence that I used is actually the same sentence for each of these. It's the number of combination of blank things chosen blank things at a time, right? The subgroup is the smaller number, and then the larger number is the group that you are selecting from. All right, so you have some problems for practicing this. This problem set is actually in 2 parts as posted. So make sure that you do all of the problems that are there, and then the answer key will be up for you next time we have class. Thank you so much.